Yes, okay. So my name is Dawit Birhanu. I'm TME at Cisco. So I'll be presenting BGP techniques for service providers. So the main objective is just cover BGP basics, discuss scaling techniques and best practices. I would like to acknowledge Philip Smith, who originally developed this tutorial. So we are just continuing that tutorial. He did most of the work. I just updated it a little bit. There will be a self-guided lab available, practice lab available, and we'll give you directions or guides on how to use the practice lab. We'll distribute the guides, so it's not going to be, we are not going to do the lab during this session. It's just something that you can do for the next 1 week. We'll keep it up for 1 week, and you can practice anytime during that 1 week. And you'll be assigned a lab pad at the end of these sessions. We'll give you the pad number and a link to the lab guide. So the agenda is, this session is divided into 2 sessions, the 101 and 102. So the first session until 3:30 will focus on BGP basics, BGP scaling, and communities. And then we'll discuss about the lab logistics just briefly. And second session will focus on BGP deployment and best practices. Okay. So the first section will cover what's BGP, BGP attributes, BGP's the best path selection algorithm, and how to apply BGP policy and BGP capability exchange. We have a lot of topic to cover, so we'll be going quickly through these slides, so I apologize for that. So what's BGP? BGP is a routing protocol used for exchanging routes between different autonomous systems, although it can be used within just a single autonomous system. It's described in RFC 4271 and several related RFCs. The IETF working group is Internet Domain Routing and Secure IDR. So the two are the main working groups, and you have the links there in case you don't have those links. So autonomous system is the cornerstone of BGP, and we'll discuss about the autonomous system. So what's autonomous system? It's a collection of networks within a single administration. They have a single internal routing or IGP, Interior Gateway Routing Protocol. And usually they are under a single administration, and they have, it has a consistent policy within that system. Typically it will have autonomous system number, either a 2-octet or a 4-octet, and we'll discuss that later on. So autonomous system numbers, the 2-octet AS number ranges from 0 to 65,000. And the 32-bit range is from that up to the power of 32, which is about 4 billion. And the 0 and 65535 are reserved. And there is also some block reserved for documentation purpose to avoid confusion, so that people don't just copy and paste a real autonomous system number. And there is also a block set up just for private autonomous system numbers. The autonomous system numbers are distributed by the registries. So you can get autonomous system numbers from the registries, either the 16 bits or the 32 bits autonomous system number. So to come back to the BGP basics, so BGP, the protocol runs over TCP, port 179. It uses a distance vector. It's a distance vector protocol. Peering is the cornerstone. So you'll have peering within a single autonomous system or between autonomous systems, and we'll discuss that. So that's internal and external BGP peering, and it uses incremental update. So it doesn't just dump the entire route every time it does updates. So obviously when you start, you'll get the full update depending on the policy, but as things change, you get incremental updates, or incremental advertisements or withdrawals. Another term that you need to be familiar with, DMZ in this context means, in the BGP context means, the shared network between different autonomous systems. So in this case, the link between A and C is a DMZ, or the broadcast network between B, D, and E is also a DMZ. So, and there are 3 autonomous systems. So the general operation is BGP learns multiple paths via internal and external BGP peering, and then it selects the best path based on best path algorithm, and then installs the best path into the routing table, and then advertises the best path to neighbors, to external neighbors as well as internal neighbors. So we have both internal and external peering, or use of BGP internally and externally. With iBGP is normally used to carry internal routes like customer prefixes, as well as internal infrastructure prefixes. But eBGP is used to advertise summarized prefixes, essentially, or aggregated prefixes, and exchange external routes. So here is a conceptual representation. So here you have 4 autonomous systems interconnected linearly, and within each one of them there is inter-gateway protocol running within the network. So those are separated. They do not talk to one another, the IGPs between autonomous systems. And there is external eBGP between the autonomous systems, and there is internal iBGP within the autonomous systems. So between BGP speakers of different ASs, you will have eBGP, and it's usually used on a directly connected interface, and you don't run any IGP interior gateway protocol on that DMZ. So those are the DMZ links. On the DMZ link, you don't run IGP protocol. You only run eBGP. So iBGP is between routers running the same autonomous system. iBGP speakers do not have to be directly connected. The reachability between iBGP speakers is taken care of by IGP, Interior Gateway Protocol. So they don't need to run, they don't have to be directly connected. But there's a requirement to be fully meshed, and we'll discuss that later on, how to mitigate that scalability issue. It is topology independent, so you just run, because it runs on top of TCP, and it uses IGP as to reach one another between the routers. It doesn't depend on the topology of the internal network. Okay. The peering between iBGP speakers, or the peering between BGP speakers within the same autonomous system, is typically done using a loopback IP address. You can do it using interface IP address, but if you do that, whenever the interface flaps, then the peering flaps, which is not really necessary, and it has adverse effects. So BGP peering within an autonomous system is done between loopback IP addresses. So the key for BGP is each update or each route has attributes. And there are different attributes, and those attributes are used for path selection, policy enforcement, signaling information, and so on. And we'll discuss each one of them. So one of the key attributes is AS path. AS path is the path traversed for the update to reach to this router or this autonomous system. So it is used to decide on the base path. Longer path means less preferred than shorter path. When it says path here in terms of the number of autonomous systems it travels. Although you can, with BGP, there's a lot of policy flexibility, so you can override that. But that's usually done with the amount of paths is used as a path selection. Second one, and very important, is loop detection. And we'll see that how that's done. But here you can see that the route received in AS400 has two different routes received there, and you'll see the AS paths. The first one has 300, 200, 100. It's usually the last one is where the routes originated, and the first one is where the immediate autonomous system. So for this case, the route originated in AS100 and it's received from AS300, and it has gone through AS200. So with the introduction of a 4-octet autonomous system number, for a long time, even today, most service providers use just a 2-octet autonomous system number, but that's running out. So a 4-octet autonomous system number is being introduced, have been introduced for quite some time. And when you have a 4-octet autonomous system number, and if you have a router that doesn't support 4-octet autonomous system number, then it has to be replaced with a reserved address, which is 23456. So 23456 signifies an autonomous system that has that is a 4-octet autonomous system, but is not understood by a 2-octet a router that doesn't support a 4-octet autonomous system number. So the loop detection, the basic principle in loop detection is if a router receives an update that contains its own autonomous system number in the AS path, then it is considered a loop and the update will be dropped. So if you look at in this example, autonomous system 100 is receiving 180.10.0016, which was originated from itself, and it has, in the update, it has its own AS number. As soon as it detects its own AS number, it drops it. So it will not take that update. So that avoids route looping. So it's used for loop detection. The other important and mandatory attribute, BGP attribute, is next hop. Next hop tells BGP what is the next hop to reach to this destination. So usually that next hop is known via IGP, and a recursive lookup will be done to say, first do a lookup, it gives you another route, and then you look that route in IGP, and it gives you that outgoing interface, and you send the traffic out that way. So next hop is important from that perspective. So next hop in the case of eBGP is the peering address. So for example, if you look at this, B has received 2 updates. Sorry, C has received 2 updates. The same thing with B. B has received 2 updates. In the case of B, the next hop points to 150.10.11, which is the peering address of B to the eBGP peer where the route is received. But when the route is sent over iBGP peer, normally, by default, the next hop is not updated. So it's the same next hop is propagated. So C also receives the update with the next hop of 150.10.11 and keeps that same next hop. So which means C has to know about 150.10.11 in its IGP table. And usually that's not desired. And we'll see later on how to override this default behavior. Okay. So in this particular case, this is for iBGP learned routes. So when router, in this case, take for example router B. When router B injects routes for 121.104.24 and 121.254.2/32, it will, sorry, that's in IGP. When it injects 120.110/24, it will inject it with the next hop set to itself. Itself means its loopback interface IP address. So when the other routers receive, the next hop will be the loopback IP address of B, which is 121.254.2. So for iBGP learned routes or routes originated within that autonomous system, the next hop is set to the loopback IP address of the router that originated the route. Third-party next hop, this is rarely used, but it's important to understand how it works. So in this particular case, 3 autonomous systems, A, B, and C, routers A, B, and C, which are in 3 different autonomous systems, even though only 2 autonomous systems are shown here, are peering with one another with eBGP. When they peer with one another with eBGP, C is peering with A and B is peering with A. Now, if by default it uses the peering IP address, so if B uses the peering IP address for routes 120.186.10, it will first send that route to A, that traffic to A, and then A will send it to C. But this is a waste of bandwidth. So when this is a shared network, when A advertises the route to B, it will change the next hop to be the third-party next hop, which is the next hop of C. Okay. So best practice for next hop. So the default for eBGP is the default for BGP is not to change the next hop when it's advertised via iBGP. But with this, it means that you have to inject the interface address into IGP. But this is a lot of overhead for IGP. It will also create a little bit of instability. So the best option is to change the next hop to the loopback IP address of that router, so the peering router. Okay. Okay. So in summary, IGP is used to carry the next hop for BGP. So in some cases, it's possible that BGP may carry the next hop for BGP, but eventually it has to recurse back to IGP. So IGP carries the next hop for BGP. Recursive lookup is used to do a BGP lookup. So the BGP lookup gives an next hop of IGP, and then an IGP lookup will take care of the actual outgoing interface. So it unlinks, this behavior unlinks BGP from the actual topology of the network, the internal network. Okay. Another BGP attribute is origin. This is historical in nature, in that originally the EGP, which is another EGP protocol, predates BGP. So if the route was originated from EGP protocol as opposed to BGP, it will have a different origin. So there were 3 types, IGP, EGP, and incomplete, and there are still 3 types, but EGP is not used because there is no router that runs EGP nowadays. So there you have 2 types of origins, IGP and incomplete. IGP is used if the route is injected using a network statement, and incomplete is used if a route is injected into BGP by redistributing IGP into BGP, or by redistributing static route into BGP instead of using a network statement. So the network statement is a preferred one, so during route selection, IGP will be preferred over incomplete during path selection. Another attribute is aggregator. So in BGP, when an ISP receives routes from other ISPs, the ISP can aggregate those routes and advertise. It's rare, normally, if there is an agreement between the downstream ISPs and the upstream ISP can aggregate multiple ISPs and advertise. It's good for internet, but they have to have an agreement. So in that case, when a BGP router aggregates routes, it has to convey the router that aggregated that route. So it puts its IP address as an aggregator to that route. Local preference, this is very important. It's used for influencing how traffic exits the network. So let's say route is, let's say 160.10.00.16 in this case is advertised through 2 different paths. But AS400 may want to prefer a path through B instead of A. In that case, when AS400 receives the update through B, it will set the local preference to 800 in this particular example. And when it receives it from D, it sets the local preference to 500. When C receives the route, it will pick the path received via B instead of via C, because the route received via B has a higher local preference, and higher local preference is preferred. So it is used to influence how traffic exits the network. And traffic will go that way. So it is non-transitive optional attributes, which means it is used within a single autonomous system. It's not advertised outside that autonomous system. So in the previous example here, B sets the local preference, A also sets the local preference. That local preference is advertised along the route to C, but when C sends updates to another router, to another eBGP neighbor, it will not set the local preference. It will remove the local preference. So local preference is transitive and it's optional. It's non-transitive, sorry. And it's used to influence how traffic is going out of the autonomous system. Okay. The opposite of local preference is multi-exit discriminator, or MAID. It's used to influence how traffic is received into the network. So if AS200 in this particular case prefers receiving traffic through D instead of C, it will send, in this case AS201 prefers receiving traffic destined for 120.68.10 coming through B instead of A, then it will set a lower metric for, AS200 will set a lower metric for routes updated through D and a higher metric for routes sent out through C. So the MAID is sent on eBGP update. So as opposed to local preference, which is sent on only on iBGP update. MAID is also non-transitive. So you send it to the next autonomous system, but the next autonomous system will not send that same MAID value to subsequent autonomous systems. It will only use it for itself. It may send another multi-exit discriminator, but its own, not the one received from the upstream service provider or the other service provider. Okay. And another important thing for MAID is MAID is considered as a metric, so lower is preferred than higher. So as opposed to local preference where higher is preferred. Watch out for metric confusion. When the RFC was first, when BGP was first specified, it didn't specify the default value for MAID. MAID is optional. So it doesn't specify what MAID value to set or to assume for a route that doesn't have a MAID associated with it. So some vendors assumed 0, some vendors assumed the maximum, and that created a confusion. Later on, it was rectified. There are different RFCs not listed here, but still, you can have a router that doesn't adhere to that RFC because that's a more recent RFC. So you have to make sure that the right value is followed. The default should be 0. If you don't receive a default value, it's 0. Most vendors give you a knob to force a default behavior. So you can say if it is a meeting made, assume 0, or if it is a meeting made, assume infinity or the maximum. Another very important attribute is community. This simplifies configuration management, application of policy. It is used to classify routes into communities or into classes, essentially. So it is a 32-bit integer. It is usually specified in a colon format where the first one is the local autonomous system number, but it can be anything, but usually it's used with the local autonomous system number. And the second one actually identifies the class or the community to which a route belongs, or a prefix belongs. A prefix can belong to one or more communities, or it may not have any community at all. So it's used to group destinations. Once you group a destination, then you can apply policy on the group instead of on specific prefixes. So that's where the scalability comes, and it simplifies the configuration or configuration management. So here, just to demonstrate that, it shows you without community how it works, and with community how it works. I'm trying to find out how much time is left. Okay. I'll just use mine. Okay. So in this case, without community, let's say first you have this scenario, so which means you have 160.10.0.0.16 coming in, and you accept it, and on the peering to ISP 400, you want to allow that prefix to go out. So you have a prefix list. You add that prefix to that prefix list. And then you have another customer coming. When this customer comes, you have to update your prefix list on that peer in addition to the actual customer configuration. So you have to touch that configuration. And changing a BGP policy has impacts. Whenever you change, you may, depending on the scenario, you may have to soft clear the BGP peer, which has to update the BGP table. So it has impacts. So you don't want, you want to avoid as much as possible making changes anyways. So now you have a prefix coming in, but you don't want to allow that, so you don't you don't add any entry for that. Now with a community, what you do is whenever you receive a route, you associate a community with it. In this case, 300:1. And you will have a configuration on ISP1 that says any prefix with the community 301 allow it to go out on this peer. Now, when you have another customer coming in, you just set the community. You don't need to change the BGP policy going out from E to F. Now, when you receive another update and that you don't want that update to go to AS400, now you set with a different community, in this case 300:1, and that update will not go out of that peer, the EF peer. So you can see that it simplifies the configuration management tremendously. There are several well-known communities, and so the most common ones are, is that the remaining time? Okay. So the most common ones are no export, and we'll see what that means. It means you don't advertise to another autonomous system. No advertise, don't advertise to any peer. No export subconfederation, don't advertise to a subconfederation. We'll discuss that later on. And no peer means don't advertise to a bilateral peer. So in the case of no exports, in this case, if you apply, if the route has a no export community associated with it, then it will not be sent from AS100 to AS200, or from any AS to any AS, because it has the no exports. If it is no peer, you will not advertise to any peer at all. Okay? So what about a 4-byte autonomous system number? It is, it's defined in RFC 1998. Sorry, the 1998 defines how the community is defined, which is a 2-octet ASN number and a community number. But when you have a 4-octet ASN, what do you do with it? Because community is just a 32-bit entity, so you cannot split it into 2 different values. So some, they just continue with some predefined value as it is. Others have started using 2, 3, 4, 5, 6 as the ASN number, and others are waiting for the 4-octet extended community generic to be implemented, that draft to be implemented. So again, community is an optional attribute, but being careless can create confusion. It's very important to know, so some vendors advertise communities to iBGP peers. Some vendors advertise communities by default to eBGP peers. So you have to know the implementation. The standard doesn't mandate sending updates, so it is you have to know your vendor's implementation and make sure that if you want to send it, it is being sent, and if you don't want to send it, it's not being sent. Okay. Path selection, this is very important. So to understand how it works, there are some variations between vendors, but the standard also specifies what the preferences. But in addition to that, vendors also add additional features. So here we'll just discuss the general path selection algorithm. So the key is you do not consider a route that whose next hop is not reachable. So if a path has a next hop that's not reachable, then you just discard it. You don't use it. You do not consider a path that has the highest made value, which is 232 minus 1. So you also discard that. Then comes the selection algorithm. The third one, which is the first selection algorithm, the first selection criteria is highest weight, and that depends on the vendor. It's not a standard. So it's an administrative value. You can, depending on the vendor, Cisco uses the weight. So if you configure a weight, then it will override all other criteria. Most people don't. But if for administrative or migration purpose, you need to configure that, then you can configure it. The next one is local preference. We have already discussed that. So the highest local preference wins. The next one is locally originated route wins. Locally originated means locally originated on this router wins, because that's obvious. If it is originated from this router, it should have higher preference. The next one is the AS path length. If it is a shorter path is preferred over a longer path. Of course, in most of these cases, you will have knobs to tweak the selection algorithm. But this is, so in this particular case, you can use BGP-based path, AS path ignore, and it will ignore AS path in the algorithm. But that's uncommon. The next one is origin code. IGP is preferred over incomplete, and it's preferred over EGP. EGP is not common, so you can ignore that. So if you ignore that, then a route that is injected using a network statement is preferred over a route that is redistributed. That's what the origin means. The next one, yes? Yeah.
I don't know this. Oh, it works now.
Okay, it works.
Yeah, my name is Bechet Sarikaya from Huawei. I'm confused about this IGP and iBGP. Are they the same thing?
No. So iBGP is internal BGP. IGP is interior gateway protocol. So the interior gateway protocol is like OSPF, ISIS for service providers, and enterprise, they use RIP, IGRP, and other protocols. But the two main IGP protocols are OSPF and ISIS. So they are only used within the autonomous system. iBGP is part of BGP, but it's used for internal peering. So peering between BGP-speaking routers within a single autonomous system. Okay. So the next one is a lower MAID value is preferred over a higher MAID, and MAID is only considered for a route that's received from the same autonomous system. If a route is received from two different autonomous systems, it will not be considered, the MAID will not be considered, unless you override it with a knob. In this case, BGP always compare MAID. But there are other knobs as well. But by default, MAID is only considered for routes received from the same autonomous system. Otherwise, it will defeat the purpose. But some people want to use it for routes received from multiple autonomous systems. In that case, you can use that knob. The next one is prefer eBGP over iBGP paths. So if you receive the same routes over iBGP and over eBGP, you would prefer the one received over eBGP. Remember that this is probably for external route, because for internal route, the AS path length is 0, so that will override the eBGP, iBGP. It's only when the two are the same, when the AS path length is the same, the MAID is the same, the local preference is the same, then you prefer eBGP over iBGP. If all that is the same, then you look at the next hop and the IGP metric for the next hop. So the lowest wins. If those two are the same, then you take the router ID, the lowest router ID of the originator, so of the route reflector. If that's not the case, then you go to the shortest cluster list, and we'll come to that. That's for route reflector again. The last one is the lowest neighbor IP address, where you received the route, and that's always unique. So you pick one, that one. So the key thing is in a multi-vendor environment, you have to know the differences. There are slight variations. So it's very important to know the differences. They all follow the same, the standard, but they have additional tweaks, and additional defaults. So it's good to understand that. And it's important to avoid the made confusion. Okay. So applying policy. So why do we apply policy? One, we want to block some prefixes that we don't want to receive. We want to block some prefixes that we don't want to advertise. Second, we want to influence traffic, how it is sent, traffic engineering, how traffic flows. So in the case of ISPs, nobody just plug and configure eBGP peering and done. That's not the case. It is heavily policy oriented. So they need to control when they peer, who they peer, what routes they receive, from which peer, and how to load balance also for traffic engineering. So we'll see each one of these. So how do we apply policies? It's usually using some kind of route policy language, and by manipulating the attributes. You set the made or the AS path lengths. You can influence the AS path lengths. There are ways to increase the AS path lengths by prepending multiple ASs, by changing the local preference, by changing the weights. Also, you can filter based on prefixes, based on community, based on AS paths. You can say if this update is coming through this AS, I don't want to receive this path, or I want to have less preference for that route, and so you can change the preference for that route. So it is by setting and by setting values as well as by filtering based on different attributes. So the BGP attributes are useful from that perspective. So most implementations, that means vendor implementations, have tools to achieve this, like prefix lists, AS paths lists, AS path manipulation, language, regular expressions, community attribute settings, community attribute matching mechanisms, and some kind of programmatic language to do the policy as well. Okay. Any questions? BGP capabilities. So this is extending BGP. So there are different BGP capabilities. When BGP was first introduced, it has the bare minimum protocol, and then other features or other capabilities were added. As those capabilities are added, BGP speakers have to understand who supports what, and that's negotiated also. So the capability exchange is documented in RFC 2842. It is used when the session is established. When a BGP session is established, they will exchange capabilities. They will know who supports which capability, and they'll negotiate and settle down on the ones that both of them support. And the capabilities number is assigned by INA 0 to 63, is by consensus, IETF consensus, and then 64 to 127 is on first come, first served basis, and 128 to 255 is reserved just for vendor specific. So these are the different BGP capabilities. 0 is reserved. 1 is multi-protocol extension, and you can see the list. We'll go through each one of them, so I'll go to the next slide. So the multi-protocol extension, so the multi-protocol is, in your case, in this room, BGP is used mostly for IPv4 unicast. But BGP also supports IPv4 multicast, IPv6 unicast, sorry, here it's IPv4 and IPv6 unicast, typically. But BGP is also used for IPv4 unicast, multicast, for VPLS, for multicast tree distribution, for a number of other functionalities. So that is supported in BGP in multi-protocol extension. Second one is an important one that we'll cover here is route refresh. This also reduces the churn required during policy change, and we will see that later on, so we'll cover that later on. The third one is the 4-octet ASN number support. So when the two sessions come up, they will exchange capabilities, and they will know whether both of them support or not support 4-octet or ASN. And we'll also cover that one later on. And there are a number of other capabilities being developed, and most of them are implemented even though they are not yet full standards. So BGP scalability techniques. So we'll discuss different techniques that are used for BGP scalability, including dynamic reconfiguration, which is also route refresh, and you will see how that's used. We'll look at route reflectors, which is very, very important for scaling the number of peers required. BGP confederations, that's also required for scaling the number of peering, the full mesh peering requirement, and then deploying 4-octet ASN. Okay, so I'll skip here. So current best practice is to use route refresh, and we'll cover that shortly. It's very important to use configuration templates because it reduces errors. Update groups. Some vendors do dynamic update groups, so you don't need to do any configuration per se in that case. But if your vendor doesn't support or your software doesn't support the dynamic update groups, then you have to think about that because that improves scalability a lot. Route reflector is very, very important. We'll discuss that. Route aggregation, that's also very important, not just for a service provider, but for the entire internet. So we'll also discuss that. And deploying 4-octet ASN. We are running out of 2-octet, so that's important, and being able to support 4-octet ASN is important. So going to route refresh. Why do we need route refresh, and what's the problem it's trying to solve? So if let's say you have a BGP peering where you say, I want to accept this set of prefixes based on different attributes, either community or ASPAS links or prefix lists, and then you will say, I don't want to accept this set of prefixes. Or you may want to say, I accept these prefixes with this local preference. I accept these prefixes with this local preference, and so on. Once you apply that policy, for one reason or another, at some point, you wanted to change that policy. When you change that policy, now, remember that when BGP is incremental, which means it only advertises any new changes. So the ones that you received last time, if you rejected them, it's not in your routing table. Now, if you want to add them, then you cannot add them without bringing down the peer and reestablishing the peer, which is called hard reset. That's not desirable. It will cause the route churn, not just in that autonomous system, but across the internet. So to counter that, some vendors came up with a soft reset, and the soft reset is when a router receives updates, it keeps the updates received even though they are dropped by policy. It keeps them in table, in memory, and whenever a policy change is applied, it will reapply the policy change to those internally stored updates so that it doesn't require resetting the peer, doing a hard reset. But that would require a lot of memory, router memory, because on each peer now you have to keep routes received from that peer. If you have 1,000 peer, then you have to have 1,000 times the number of routes you receive from each peer. That's a huge amount of memory and CPU churn. So instead of that, the preferred option is route refresh. Route refresh is both routers agree that they support route refresh. So once you do that, whenever there's a policy change, the router that's changing the policy will send, please do a soft reset, and the other party will send the full update to this router, and this router will reapply the policy. So it doesn't need to keep the routes in memory. So that's basically the main motivation for it. Okay. Scaling iBGP mesh. So think of, remember we said that within a single autonomous system, all routers have to be fully meshed. That means each router has to peer with every other router. The reason for that is the rule. So the reason for that is to avoid route looping. In the case of when you cross multiple ASNs, you will use the ASN number to detect loops. But within a single system, autonomous system, the principle is once you receive a route from eBGP, you advertise it to all your iBGP peers. But if you receive a route through iBGP, you don't advertise it back to iBGP. You only advertise it to eBGP. That way you avoid loop. But to do that, all BGP speakers within a single autonomous system have to be fully meshed. But that's a huge problem. That's the n times n minus 1 over 2 scale problem, right? So if you have 100, if you have 1,000 routers running BGP, then you will have 500,000 peerings to manage. That's a huge amount. So there are two ways to scale for this. One is route reflector, which is the most commonly used and probably the most efficient. The second one is confederations, and we'll discuss both of them. With the route reflector, now the rule on the route reflector is relaxed. The rule in the route reflector becomes if a route reflector receives a route on iBGP from a client, from a route reflector client, then it can send it to any peer, both to another client, to a non-client, as well as to eBGP peers. If it receives a route through a non-peer, then, a non-client iBGP peer, it will advertise it onto a client iBGP peer. It can advertise onto a client iBGP peer and, of course, to eBGP peers. But a non-route reflector, if a router is not a route reflector, the rule still remains the same. That means if it receives iBGP updates, it will not send it back onto another iBGP updates. Okay? So basically what will happen is each router will peer with one route reflector or two route reflectors for redundancy purpose, and then the route reflectors will have a full mesh between themselves, or you can have even a hierarchy. So that way now the scale is reduced. You are subdividing the network. In this particular case, you can see it is subdivided into 3 different clusters. In each cluster, each router is connected to one route reflector, the clients, and then the clients are fully meshed in the triangle in this case. So the topology is you divide the backbone into multiple clusters, and then you will have one route reflector in each cluster, and each client will connect to the route reflector. Usually, a client will connect to 2 route reflectors, which means it belongs to 2 clusters. You still have one IGP that doesn't change, so you will have a huge scalability. So now with the route reflector, how do we avoid looping? It uses originator ID and cluster list. A cluster, usually the cluster, when a route reflector receives a route and sends an update to another peer, it will set its own cluster ID as, it will append its own cluster ID and send it. So if that router receives the same cluster ID, then it will drop it. So it uses the cluster ID in the cluster list to detect loops. Redundancy is very important, obviously. So typically, you'll have 2, in some cases 3 route reflectors for each client. So usually, you'll have, let's say, suppose you have 20 clients and 2 route reflectors. Each of the 20 clients will appear with both route reflectors. And then you can have a hierarchy, or you can have other clusters, and then the clusters will have a full mesh. So redundancy is very important. So here is an example of redundancy. So here, this example shows 3 POPs. Each POP has 2 route reflectors, which means 2 clusters per POP. So even though it says here cluster 1 and 2, you actually have, in effect, you have 6 clusters in this case. So 2 clusters per POP. Each client connects to 2 route reflectors in each of the 2 clusters. So the benefit is it solves the iBGP mesh. It doesn't impact packet forwarding. It has a little bit impact in that the route reflector makes a path selection and sends the best path to the clients. So it's not that the clients receive all the paths, but still the forwarding, the eventual forwarding doesn't get affected. It's an easy migration to go from a full mesh to a route reflector topology, and you can have multiple levels of route reflectors. So the migration is usually very simple. You can start from a small cluster and expand throughout the network. So this is showing an example of migration. In this particular case, it's just doing the route reflector within that POP. So it creates a route reflector, D becomes a route reflector, and everybody, E removes all its peers and just peers with a route reflector. Same thing with F and G, but B, A, and C still remains in a full mesh. And you can upgrade them later on to become part of the route reflector topology. But the key is it is incremental. Confederation has the same effects, but in a different way. It's used to deal with a full mesh problem. In this case, it creates multiple sub-confederations. Each sub-confederation becomes its own autonomous system. It usually uses a private ACE for the sub-confederation. It is still one autonomous system, but with sub-autonomous systems. It uses just a single IGP. The IGP doesn't change. The sub-confederation is not visible to the outside world. It's only for internal use within the service provider, within a single autonomous system. Okay. Here is an example. So here you have AS200 with 3 confederations, AS65530, 65531, and 65532. Usually the private ASN number is used for confederation. And you have eBGP between confederations and iBGP within the confederation. You can have iBGP mesh within the confederation, or you can even mix route reflector in the confederation itself. So here is an example configuration for confederation. So in this case, first you say, I have this confederation, which is 65532, has 2 sub-confederation peers, 65530 and 31. And then for each one of them, and you have the confederation ID, the confederation identifier, which is the AS number for the entire autonomous system. So the AS sequence number is very important to understand here. So if you look at the route received from a peer, from outside peer, from peer 200, AS200, 180.10.0016, when it is advertised to the next confederation, to confederation 65004, it has 200 and then 65002, which is the confederation AS number. And then when it's advertised, that to the next confederation, it will add additional confederation ID. But when it is eventually advertised to the outside world, the confederation AS number is replaced with the actual AS number, which is 100 and cent. So it's only used for internal purposes. Key for confederation is, so the external peers still refer to this router as with its own AS number, but the internal peering is done with the confederation AS number. So peers in a different AS prefer local preference made, everything remains the same. So external peers refers normally to external ASs. So the key differences between the two, both of them can be used for internet connectivity. They both support multi-level hierarchy. They both support policy control. The key difference is in terms of scalability. Route reflector scales better, arguably, and also from a migration perspective, route reflector has lower migration overhead compared to confederations. But in some cases where you are absorbing, one service provider absorbs another service provider, confederation may be a better choice. So let me check what's, we're doing good. Checking just the slide number. Okay. So 4-octet ASN, it is documented in 4893, RFC 4893, and those related RFCs that you see there. And it reserves 2, 3, 4, 5, 6 in a 2-octet ASN to represent a 4-octet OSN in a 2-octet ASN world. So a 2-octet ASN refers to, or a 2-byte ASN or a 16-bit ASN refers to the range 0 to 655535. A 4-octet ASN refers from 65,000 to 4 billion. And a 4-octet ASN pool refers to the entire range from 0 to 4 billion. So the key terms. You can get a 4-octet ASN from registries, so there has been changes, but now there is no difference between how you get a 4-octet and a 2-octet ASN. Same process. So representation. Now, it's very difficult to represent a 4 billion number in a nice way. So some people want to change that and use a dot notation. So split the ASN into 2 octets, two 2-octets, instead of one 4-octet number. So as a result, we have 3 different formats. AS plain, which is the entire 4-octet represented as one number. AS dot, which is the ASN represented as a 2 octets separated by dot, but it only represents a 4-octet ASN, and then AS dot plus, representing both a 2-octet and a 4-octet ASN in a dot notation. But when you create both AS dot and AS dot plus, creates a problem for regular expressions, filtering, and so on that you have. You have to rewrite all your irregular expressions and filtering that you use for ASNs. And this example shows you why that's the case. So how do you go from a 2-octet to a 4-octet? The key is there is no flag day. So you can incrementally go from a 2-octet to a 4-octet. First thing that you can do is just start upgrading your routers to a 4-octet, to a version that supports 4-octet OSN, and most do, and you will see that later on. Once you have that, then you can start supporting a 4-octet ASN and it will work fine. If you have a talk-to ASN, you'll continue using your talk-to ASN, but you will still be able to accept and see a 4-octet ASN paths. Okay, so the key is when you have a router that supports a 2-octet and another router that supports a 4-octet, and the router that supports the 4-octet has a 4-octet ASN, then when you configure the router that doesn't support 4-octet ASN has to be configured to talk to AS number 23456 instead of the actual ASN number, because it doesn't understand a 4-octet ASN. That's the key from a configuration perspective. But that's if you have a router that doesn't support a 4-octet ASN, which is very rare nowadays. Okay, so this is the compatibility mode. So when you have that, a 2-octet ASN always sees 2-octet ASN paths, and the 4-octet ASN number is replaced by 23456. And this demonstrates that example. In this example, you can see that AS321 has received updates from AS 80,000, but the 80,000 and 70,000 are replaced. Both of them are replaced with 23456. So you will see multiple of that in AS paths, because each one, it represents just a random, not a random, a specific 4-octet ASN. So you may see in AS paths multiple 23456 appearing in the AS paths. It doesn't indicate a loop, and it doesn't fail loop detection. Loop detection is when you see your own ASN in received paths. So this is not a loop. So what has changed? So 2 attributes. We used to have AS paths. Now a new attribute, AS4 paths, is introduced. And in addition, AS4 aggregator is also introduced when you do route aggregation. And also a new AS number is reserved, 23456, as AS trans. Okay. What do they look like? So here is AS plane notation in AS plane format. So the top one is in AS plane format. In the AS plane format, you will see the full AS paths information. In AS dot format, you will see 2.0 and 3.5 instead of that long number. So it makes the number shorter. So that's the reason why some people wanted to use the dot notation, because it simplifies the representation. So how does that same path look like in a 2-octet world? Just replace those 4-octet ASNs with 23456. Okay. So what is the impact of not supporting a 4-octet ASN? So one of the problems is you don't really know the exact path it's taking, because every 4-octet AS autonomous system is represented as 23456. So that's the main problem, and it's difficult to deal with. And another one is incorrect net flow summary if you use net flow based on AS number. So as you can see, most vendors, there's a complete list is shown in that link. And you have most vendors have been supporting it for quite some time, as you can see from here. Okay. So service providers' use of communities, how service providers use communities to make life easier. We have already seen that, but some additional techniques. So usually communities are used at the edge, either at the customer edge or at the border edge or internet edge. So whenever you receive routes, you classify the prefix or the route into a class or into one or more communities, and then you assign those communities to that route. And then internally, a policy is used based on that community to either block that update to go out somewhere, or increase the route preference, or advertise it or block it into another peer, and so on. So let's see an example for customer edge. So in this particular case, it tries to demonstrate how an ISP that has 3 different internet connections, IXP inter-exchange connections, private peering, which is another ISP in the same region, and transit provider to the entire internet. Now, a customer may have option to buy connectivity to the entire internet, or only to inter-exchange carriers within that same network, or to some private peers. So a customer may purchase, let's say a customer has another connection to another peering, and they may only prefer the private peering purchase instead of the whole internet. So depending on that, customers are classified into different classes. So customers who buy the whole internet are not assigned any community. Customers who buy IXP connections are assigned 120-100 community, and the customers who buy private peering are assigned both. So the internet means everybody gets the internet, and some customers can get, in addition to that, IXP connections, some may get the private connection as well. So here, when a customer route is received on an aggregation router, it is tagged with appropriate community based on what the customer has purchased. If the customer has purchased everything, they will have all the communities. If the customer has purchased just the inter-exchange, then they will have the inter-exchange community, and so on. Then based on that, when their routers will be advertised to the appropriate prefix, or they will receive to the appropriate prefixes. So it is used both for inbound and outbound traffic. In this case, this is for inbound traffic, so for outbound traffic. Now, you don't need to change, as customers are added, in this case, you only have one policy on the border router, and you don't need to change that policy whenever you add a customer. You just classify the customer into a specific community, and you will not need to change the policy on the border router, which minimizes errors. Change always has a risk of making an error. It also could impact route updates and create churns as well. Okay, so that's what's stressed here. Now, in this particular case, it is for internet edge. So that is, you classify prefix received on the internet edge so that outgoing traffic is impacted in this case. So ISP has 4 types of BGP peers. It can have a customer BGP peer. For some customers, only for multi-home customers, and we'll discuss about that later on. And for inter-exchange peer, and then private peering. So inter-exchange and private peering are similar, except that the inter-exchange is usually done in a multi-tenant scenario. So the inter-exchange carriers, basically. The transit provider, that's where you get your full internet connectivity. And the prefix received from each one of these is classified in different communities so that they are advertised to the customers accordingly, based on what the customers has purchased. So community assignments. So customers who purchased, so in this particular case, actually, customer prefix are assigned a specific community, inter-exchange prefix are assigned another community state, and private peer prefix are assigned a different community state, and based on that, you can assign different policies. So again, no need to change customized filter for each customer or for each peer. You just classify them into classes. Okay. So ISP BGP communities, one of the problems is there are no any recommended communities, but some service providers document their community setting or what communities they expect from their customers or what communities they will advertise to their customers if you are peering with that particular service provider. So that's listed here. Here is an example for a Sprint. I'll just discuss the one for Sprint, and then you can go with the rest. You can look at the rest. So in this case, for example, first one, do not advertise. So if you don't want Sprint not to advertise your prefix, you can just tag it with that particular community. You can say a string, and then this is so this is for different regions, Asia, Europe, and so on. So it shows you the different ASs, the different advertisements going different ASs. So here is another example for NTT, and you can go through that also, and for Verizon and others. So I'll just skip through that. They are different. It's there for your reference, and you can actually go to the links. The links are already shown there, and look for yourself. Okay. So any questions? Okay. So I'll discuss about the lab, and then we'll open up for questions. So we have a lab, and we'll distribute paper where you will have access, how to get access, and your pod number. So the lab is set up in a virtualized environment, and it uses iOS XR, Cisco iOS XR. It has a 6-router topology for each pod. We have, I think, about 14 pods. So you'll have access to one of the pods. You can have access to one of the pods where you'll get the pod number. And the lab guide is also included in that documentation, and you can go and do practice. We'll open it up for 1 week, and after that, you may not be able to log into it, but you can continue practicing for 1 week. And the guide tells you how to save your configuration, how to start the lab, and how to load the base configuration. There's already a base configuration where you have the iBGP peers already established, the eBGP peers established, and the IGP protocol already established, and the IP address already assigned. You can change those, but that's a starting point for you. And then you can apply policies as you want, and there are suggested exercises there that you can do. Also, routes are also injected from different routers. You'll see also different types of routes with different AS paths. So you can use different show commands. Also, the document includes the document linkage there. I put it in a Dropbox so that you can access it. Includes information on how, what type of exercises to execute and how to save your configurations as well. Questions? It's a quiet crowd.
Hi, my name is Bharat Ravi. I'm a master student at Georgia Tech. So I have a question about how BGP and IGP interact. Okay. So if BGP is used to announce prefixes to your peers, but let us say that I have not been announced a prefix, but I already know that prefixes within an autonomous system. What prevents me from just sending out a network packet with that destination to the router and just expecting it to be transmitted to that AS, even without a route being announced to me? Is this taken care of at the IGP level?
You mean if you are a different AS and you don't receive updates, but you try to send traffic to that router? So you already have a relationship with that autonomous system, right? Normally, so if let's say in that case, it's either a private peering or an inter-exchange peering. Some of them will also implement prefix filtering, so they will only accept traffic destined for to specific destinations from specific destinations on that peer. So they do that as well. So that will prevent it, but some of them may not do. But if you violate your peering relationship also, so you also have a paper agreement or email agreement. If you violate and they found out, they will have tools like NetFlow and other tools to collect flow information, and they can find out what you are sending, and they can terminate your peering relationship and probably even seek damage for it, right? So even though some people from the audience may comment on that, but again, it's a cooperative scenario. There are things that you can do to block it, but some of them may not implement filtering, because filtering sometimes is expensive. Route filtering or not route filtering, traffic filtering sometimes is expensive and has performance hit depending on the platform. But if you have that support, if you can filter it, it's good to implement the filtering, the traffic filtering in addition to route filtering, which is a common practice.
May I ask a quick follow-up?
Yeah.
So what happens if you do not have any kind of peering agreement and the other person does not have a filter set up and you just try to pump packets into the network?
Then you are, well, I'm not sure what agreement you will have. So if you have a peering agreement, usually it is settlement free, which means you are sending traffic and they are sending traffic to you, and there is a proportion of traffic that you have to meet. But if you don't have a peering agreement, then probably you are paying them for a bandwidth, and they are probably measuring it or receiving a flat rate. So you will still have to pay for that.
Thank you.
Okay. Questions? Okay, we are a bit early, about 8 minutes. I thought I will have shorter time, but I think we skipped through quickly. So the next one is it at 4, right? 4:30, okay. So we'll meet 4:30 here, and we'll continue with the deployment of deploying BGP and ISP networks. And we'll discuss some of those questions as well. Okay, thank you.